Okay, and now it's time for the fundamental theorem of calculus, the most important thing in all of calculus. Where are we? We're sitting here looking at this squiggle from A to B of f of x dx. And I know what you're thinking. You're thinking that is the area under the curve. That is the area of, oh, whatever the curve might be, y equals f of x. We go from A up to B. We are talking about that particular area. Now, if the curve happened to be a triangle or a rectangle or a parallelogram or some other shape that you know how to find the area of, bam, it's on. Otherwise, I know what you're thinking. You're thinking, well, I would just chop it up into, I would take the limit as n goes to infinity of b minus a over n. I'd split that b minus a width up into n equal parts, and I'd multiply it by I equals 1 up to n of, I have so much trouble with vertical lines, of, what is it, f with plugged in a plus I b minus a over n's. Well, you're right. You could use the Riemann sum. That would be a great way to do it. But there is something wonderful, wonderful, awesome, cool about this. And the story goes that once upon a time, some people came along and they looked at this sort of thing and they said, what is the derivative of that sort of thing? Because these are the derivative people, and they ran into the integral people, the area under curve people, and they said, what is the derivative of that sort of thing? Well, first of all, it's not a function. You can't take the derivative of something that isn't a function. So they made a function. They said, well, how do I make a function out of this? I could say that my new function, f of x is a function, and we know how to take the derivative of it, and it gives you the slope of the tangent line. But the new function, big F of x, is going to be the integral from 0 up to x of that function. We've used x twice, so here's the little trick. You turn the x-axis into the t-axis, and you say, this is a function of t, really just rename the variable, of f of t dt. What exactly does this mean? This means that x is now a t value, and if you have some point x on your curve, we are talking about the area from 0 up to that point. So this is the area of that. And as I plug in different values of f, I'm going to get different numbers, because if x is over here, we get more area. If x is over here, we have less area. Great, great, great. And then they said, well, what's the derivative? The derivative, everybody knows that the derivative is the limit as h approaches 0 of the function f of x plus h minus the function all over h. And if you don't know that, your Calculus 1 teacher sucked. Anyway, what is this? Well, what is f of x plus h? Well, f of x plus h, this one, is not the area up to x, but the area up to x plus h. So we want the area up to there, which I will indicate with red slashy lines. That is the area of f of x plus h. And f of x, as we just said, was that green area. So what is the red area minus the... Do I really have to do this? Of course I have to do this. Well, that shouldn't be too hard to figure out. You take this whole red shaded area and you subtract the green shaded area, and so this whole numerator is the area of that little bit here. I'll draw it like this. that little bit in there. It's practically a rectangle. Now the top is curvy just like the function, but so be it. What is the width of that? It's a width of h. It's going from x to x plus h. It's h wide. What is the height of it? Now, I know last time I said, oh, I'm all about the right endpoint. Well, this time I'm a little bit leaning toward the left endpoint. Why? Because if I had to choose between plugging x into the function to get this height and x plus h, I'd say save myself some writing. So it's sort of f of x tall, right? You plug x into this function, into f of t, and this is the point x, f of x. It gives you a height. Now, okay, it's not exactly a rectangle. It's kind of sort of a rectangle. But, look over here. We're taking the limit as h approaches 0. As h gets skinnier and skinnier and skinnier, it gets more and more rectangulish. And so we can say that this is pretty close to, especially knowing that we're taking the limit as h approaches 0 of, what is the area of that thing? Well, this area is h times f of x. H times f of x divided by h. And now, oh no, I can't let h go to 0 because we've been dividing by 0. Ah, cancel, cancel, cancel. Now h is out of the picture, and it is simply f of x. And this made the people say, what? Because we thought this was a strange, crazy function. It's no strange, crazy function. Well, it is a strange, crazy function, but its derivative is the original function. And there is some amazing, beautiful stuff in here. For instance, let's just say I can condense this whole thing down to f prime of x is f of x. You want to see that again? Travel backward in time and see it. Yeah. So, we're saying f prime of x is f of x. And let's say I wanted to find the area. Make all this go away, but don't lose the function. Let's say I wanted to find the area, as I always do, of this. I should have made that go away. From B to A. Well, big F of x goes from 0 up to x. So big F of A is the area all the way up to A. I'll use the green this time. This shaded area is big F of A. Why? Because big F is the integral, the area under the curve from 0 up to whatever you plug into the function, A. That's that. Big F of B is the area of just the part up to B. And so if you want the area just between B and A, then what we're going to say is the integral from A to B of f of x dx is f of A minus f of B. Except that I made my A and B go switch the places. I don't want to do this again. These are switched. We go from A up to B. So f of B is that big area, and f of A is that area. And so the integral, shame on me. I'm not doing this thing over again. What the heck? F of B minus f of A, where f prime of x is little f of x. And this is what is known as the fundamental theorem of calculus. It says in some sense that finding the area under a curve is the opposite of taking a derivative. Do I have a lot of room? I have a lot of room. Let's do an example with this. Let's do an example. Let's say, let me pause this for 1 second. Okay, I believe in the last assignment we did the integral from 1 to 5 of 1/2 of x squared dx. And this is tricky. We could do this with a Riemann integral, Riemann sum. We don't feel like doing that. It is just going to be f of 5 minus f of 1, where, here's the tricky part, the derivative of that function has to be the original function, 1/2 x squared. And you think, whose derivative is 1/2 x squared? Well, you might think a little bit and you think, it's got to be something like x cubed, right? Because the derivative of x cubed is 3x squared. Ooh, that's what, 6 times too much, right? Because I get the right power of x, but I want the wrong coefficient. 3 is 6 times more. So let's try 1/6. The derivative of 1/6 of x cubed is 3/6 x squared, which is in fact 1/2 x squared. Ding, 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 ding. That is our function. So f of x is 1/6 of x cubed. And so we say that the integral from 1 to 5 of 1/2 x squared dx is 1/6 of 5 cubed minus 1/6 of 1 cubed, which is 125 sixes minus 1/6, which is 124 sixes, which is not evenly divisible, but we can take a 2 out if we really feel like it, and we do, and we will get 62/3, or 20 2/3. Hey, that's familiar. Is that familiar? I guess it is. So this is the fundamental theorem of calculus. Think about how much of a pain it is to calculate y equals 1/2 of x squared and then chop this area from 1 to 5 up into, what, 8 different pieces or n different pieces and take limits and use summations and do all sorts of crazy stuff, or try to come up with something there. No. Bang. All we now have to do is get good, and this is what a lot of the rest of the semester is going to be, get good at undoing derivatives, thinking, whose derivative is this thing? And those are called antiderivatives, and we've got a lot of those coming.